Okay, so for this part of the class, you're gonna need your notebook. I'm gonna go over what normally would be like the back of my board, which would normally be like my unit map for the whole unit. We'll go over the main ideas, right? So if you see things you don't recognize, these might be items to write down, okay? So for your test on Thursday, we started out the unit talking about resistance as a quantity. Resistance prevents the flow of electrons through a circuit. And the resistance of any object depends on its material that it's made of and the material's geometry, right? So this is really easy to deal with for a wire because a wire is made of uniform material, the same material everywhere, and it has predictable geometry, right? So the resistance for a wire depends on the material, that's its resistivity, the length of the wire, and the area of the wire. You can also kind of rewrite this in your mind if you want to, as the area depends on pi r squared, because it's the cross-sectional area of this circle here, this circle. So if I do pi r squared on the bottom, I see that changing the radius has a large effect on resistance. Doubling the radius would actually quadruple the area and quarter the resistance. Would this equation be able to do things like identify how changes will occur? So if I doubled the length and tripled the radius, that would put a 2 in the numerator, put a 3 squared, so a 9 in the denominator. So you would have 2/9 of the resistance. Would this equation also be able to identify that as current flows through a wire, its electrons carry electrical energy? And that's dissipated as heat as it travels through the wire. With light bulbs, that electric energy turns into heat. And with the old filament style light bulbs, they produced so much heat that it caused the materials to heat up, and the heat would also turn into light. There we go. So we started this unit with the idea of resistance. Resistance prevents the flow of current. Current, then, in this picture, we have like an electron moving through a wire. Now, the electron moves to the left on average, but it actually moves very slow. The electron drift speed, how quickly it moves through a meter of wire, is only about 1 millimeter per second. So the drift speed of an electron is very, very slow. On the other hand, right, at 1 millimeter per second, if I needed to turn the light off in my basement, that would mean that when I flip the switch, it should take, 3 meters at 1 millimeter per second. It would take like 3,000 seconds to turn a light off. And I know that's not the case because even though the electrons themselves move slowly, the energy moves very quickly. So when I'm comparing these two side by side, I kind of made this chart so you can tell right off the bat that the drift speed, the electrons themselves move very slow, even though the energy travels very fast. Now, the energy travels fast because when the electrons repel each other, as one electron starts moving, it repels the one next to it. And that chain of repulsion, the energy carrying through the wire can go very quickly, even if individual electrons move slowly. That's why when I turn a light switch on and off, I don't have to wait 3,000 seconds for the light to turn on and off. So when we label current then, I'm going to ask you to label it in one of two ways. I could ask you to label it in the direction that the charges are actually flowing. In this case, the charges are actually flowing to the left, away from the negative terminal, towards the positive terminal. And you'd be able to tell because I'd ask you something like label the direction of charge flow. Where if I tell you to label the direction of conventional current is defined as the direction of the electric field. It travels from positive to negative. So the direction of the electric field is from positive to negative. Calculations with current. When we want to calculate current, what 3 amps of current actually means, right, is that 3 coulombs of charge pass through every second. So current, whose symbol is I and measured in amps, what 3 amps means is that I have 3 coulombs of charge pass through every second. So if I want to change coulombs, like how many coulombs of charge there are, to number of electrons, the number I need to have is this elementary charge. This 1.602 times 10 to the negative 19th C. That's the elementary charge. So if I wanted to figure out how many electrons there were, I would literally be writing into my calculator 3 divided by 1.602 times 10 to the negative 19th in parentheses. I can check to see that I've done this right because I should have a very large number of electrons. 10 to the positive 19th is a large number of electrons, right? So imagine 1, 8, 7, and then like 16 zeros after. That's quite a few. Very more than one. So there's a large number of electrons flowing through your circuit every second. 3 amps of charge. So I would take my 3 amps. That means there's 3 coulombs of charge every second. Divide by elementary charge to get the number of electrons. So then we put this all together to make Ohm's law. In Ohm's law, we want to be able to describe in words so that current is directly proportional to voltage and inversely proportional to resistance, which means the other graph you kind of have floating around in the back of your head is that if resistance goes up, current decreases, this inverse graph. And with that relationship, that current depends on voltage divided by resistance, I can actually solve for the resistance using this graph. So let's say in this example, I want you to calculate the resistance using this graph. You should be able to pick any point on the graph. And I picked the point 3, which is 3 volts, and 2 amps. Substituting in 2 amps and 3 volts, I can multiply R to the other side to get 2R equals 3. And find the resistance is 1.5 ohms. Right. So far, we know that we've got resistance. Resistance can change the current. Right. Now that we have current and how it affects resistance and vice versa, we can deal with power. Right. So power is the rate at which energy is transformed. And in a circuit, you can calculate it as power is current times voltage. So when we do power, if we want power in watts, I would want amps for current. I would want volts for voltage. And what this tells me is it tells me how much energy is transformed per second. So for instance, a 40-watt light bulb takes 40 watts of electricity and it turns it to, actually, how about I write that better? 40 watts takes 40 joules of electricity every second, and it turns those 40 joules, how about 40 joules electrical, to 40 joules heat plus light every second. So power is nice because it tells you how much energy is being transformed. If it were a motor, then it would be taking electricity and turning it into the kinetic energy of the spinning motor. If it were a speaker, it would take that electricity and turn it into 40 joules of sound, radiant energy. If it were 40 joules of electrical into my phone, then it would probably turn that 40 joules into light, almost entirely light for my phone. And a lot of the things associated with power that we did was transforming it over to energy. So we remember from Unit 5, energy, E, measured in joules, it's the ability to do work. Remember, it's the stuff that can transform from type to type. And doing work means it could move an object. Gravitational potential could move an object down a hill. Spring potential could move an object like by shooting a bow across the room. Kinetic energy is literally doing work. It is moving the object. And how we can calculate energy is power times time. So fun fact, there's two ways to do this, and I'm going to show you both side by side. Side by side, when we deal with energy, we can do this in joules or kilowatt hours. And you'd hear me specify which one, so there won't be any confusion there. If I want you to calculate energy in joules, then you just use base units. I would use watts for power, and I would need to change time from 4 hours into seconds. So for joules, that's joules, watts, seconds are related to each other. So I would take power times time, so 1,500 watts, and I did need to convert here. In this case, I converted 4 hours into 724,240 seconds to get an energy of, oh gosh, 1,071,360,000 joules. Alternate way. What if I asked you for the same thing, but I asked you how much energy does a 1.5 kilowatt motor use after 4 hours? This is the same problem with the little note that instead of calculating hours to seconds, I changed watts to kilowatts by dividing by 1,000. There's 1,000 watts in 1 kilowatt. So when I do energy as power times time, that's 1.5 kilowatts times 4 hours. And wow, that makes the math so much easier to do in my head. 1.5 times 4 is 6 kilowatt hours. This is a good one to screenshot. If you are a person that has trouble doing energy problems, like in homework 4.3, this would be a good one to screenshot. It shows you both methods, and your notes could include practice problems. As a check at the end, whichever way I do this, I should get the same, or I should get values that are related to each other. There are 3.6 million joules in every 1 kilowatt hour of energy. A kilowatt hour is a very, very, very big unit of energy. It takes 3,600,000 joules to turn into 1 kilowatt. So I've done this correctly. These two should be the same number. Let's take a look at the most recent things then. So what we did last week and this week then was we looked at series versus parallel currents. How we can tell series versus parallel from each other is series means all your resistors are connected along the same path as each other. In series, all the resistors are along the same path, And that's why they have the same current. We use series to introduce Kirchhoff's loop rule, which is a restatement of conservation of energy. What this rule says is essentially if 9 joules per coulomb leave the battery, right? 9 volts is 9 joules per coulomb. That energy has to get used up in the circuit. That means each of the resistors has to use a portion of that 9 volts, and it's used up proportionally. Whichever one has the largest resistance will be hardest to get through. So in this case, like the 25 ohm resistor would take the largest portion of the energy because it's hardest for the electrons to get through. And the 5 ohm resistor would take the smallest portion, but it better add up to 9. Over that loop, the supply puts out 9 volts, and that should get used up by the resistors in its path. So then today we added on equivalent resistance in series. For equivalent resistance in series, adding more resistors in series is like adding more obstacles. So more resistors in series is like more obstacles for the circuit. Adding more resistors increases equivalent resistance. And that causes a decrease in current. And fewer electrons traveling through every second means a decrease in power. Those electrons are carrying energy through the circuit. So if you have fewer electrons, there's less energy and less power. As a check to make sure you've done your equivalent resistances correct, in series, because adding more obstacles makes it more difficult, I'm expecting an equivalent resistance larger than the largest resistance, larger than 25. So when I plug this into my calculator, I'm expecting some number larger than 25 for equivalent resistance in series. All right. The drawback for a series circuit, though, the drawback for a series circuit is if any one of those resistors fails. So let's say the 5 ohm resistor burns out. That leaves an open path in the circuit, and so current doesn't flow. That's why homes are always wired in parallel, right? So homes are wired in parallel, and parallel looks something like this. Each individual resistor all is on their own different paths. So what sets parallel apart from series is in parallel, your resistors have independent paths. Each resistor could have a different current from each other, could have different currents. It allows independent operation. If the 5 ohm resistor burns out at this point, well, that doesn't change the other resistors. They still form closed circuits, so the current can still flow through the other parts. Homes are largely wired in parallel for this reason. The only thing you should point out, homes are wired in parallel except for one item. The one item that's always in series is the fuse. Now I'm going to put my fuse right next to the power supply. A fuse will melt if too much current flows through. So for my fuse, I want it to be right next to the power supply so that if a short circuit or something were to happen, or if I add too many resistors in parallel and this gets overloaded, that the fuse is right next to the main power supply and the electricity for the whole circuit stops instantly. It doesn't just shut off a part. We want the fuse next to the power supply so it shuts everything off at once. Right? So parallel rules then. Each path in parallel has to have the same voltage as each other. That means the 20, the 10, and the 5 would all have 9 volts. they use up 9 volts or 9 joules for every coulomb of charge that passes through. And those 9 volts came from the battery. So that along each path, the battery puts out 9 volts and the resistor uses up 9 volts. All right. And because of the junctions that occur in parallel, that's what we use to introduce Kirchhoff's junction rule, even though this is true for complex circuits as well. Kirchhoff's junction rule is a restatement of conservation of charge. This is saying whatever electrons leave the battery must go through the branches. And that makes sense to me, right? So let's say that I had, I don't know, 10 amps leave the battery. And I'm going to make up numbers. I know these aren't right. If 8 amps went along this path, I know this would leave 2 amps to go along this path. That's because charge is conserved. The electrons that flow into this junction split up into 8 and 2, but there's still 10 of them. You can imagine this as like a flow of water. If the battery pushes out 10 gallons of water and 8 of them go along the pipe for 5 ohms, then 2 of them must go through the remainder of the circuit. And maybe we get to this one and a portion of it goes up. So let's say half an amp goes this way and 1.5 amps goes the other way. That's still going to obey Kirchhoff's junction law because 1 amp flowed in, 0.5 amps flowed up. So 1.5 amps flowed left. At every junction, the current in equals the sum of the current out. Which gave us our last thing we were working on today, parallel equivalent resistance. The parallel equivalent resistance equation looks the way that it does because in parallel, adding more resistors, well, that adds more paths. It opens more paths for electrons to flow, gives them more space. Adding more resistors actually makes it easier for the charge to flow. So there's less resistance, more current, more power. That is why parallel circuits can get overloaded. Parallel circuits can get overloaded because if I add a fourth resistor up here, that's going to cause more draw of current from the battery. Imagine it's going to pull more electrons from the battery out. And if I do this, I can make the current go so high that it becomes dangerous. Right? You can overload a circuit by adding too many resistors. If you add too many resistors, you can make the resistance too low and the current too high, and all that excess power turns to heat. So things you don't want. You don't want the wires in your wall heating up to dangerous levels. That's how we start house fires. So all in all, at the end of the unit, we were looking at patterns for series versus parallel, right? So last week we did series circuits, parallel circuits, and complex circuits. Today we added on how to calculate equivalent resistance. But that brings us to the end of our unit.